Ahí.
Entonces estuvimos conversando sobre conditional expectation, sí, como conditional expectation. La conditional expectation es un concepto muy interesante. Conditional distribution. Este conditional distribution, como les decía, como concepto recién aparece cuando tenemos two random variables. For example, when these random variables are discrete, you have the conditional EMF of y given x is defined as this is the joint PDF divided by the marginal TMF of x. Conditional distribution. Continuous random variables. We are dealing with continuous random variables. This is the conditional PDF. Okay. As ratio between this is the join PDF. And this is the marginal. In this case, this is the marginal. X of y of x and y. Okay. And you know that the marginal PDF the join PDF. Okay, this is okay. Join PDF. The integration is over the x. Y. X. Integration is over the x. So when you want to compute the marginal distribution of y, you integrate over x. If you want to compute the marginal PDF of x, you integrate over 2y's. Okay. that is the conditional distribution of a random variable. This is the conditional PDF. Conditional PDF of x given y equal small y. Then there are two more concepts related to this definition. The joint PDF and the conditional PDF. Okay, that is the expectation. Expectation. We know that if x is a random, it's a continuous, okay? It's a continuous random variable. And f is a function. It's a continuous, okay? Continuous function. Actually, a sufficient condition is that this function should be a function. Okay. Anyways, continuous function, like, for example, square, or the identity, or trigonometric, whatever. Any function that we will work with. Then the expectation of f of x, this random variable, this is just the integral over the real lines of f. Then you put a small x here. Okay, I will change this because I don't want you to get confused about this function. Okay, we'll put g. Okay, g. This is g of a small x multiplied by the density function of x. Okay, that is the expectation of g of x, where this x is a continuous random variable. But what happens if we have two random variables are continuous? Bivariate random vector. Okay, if this is if x and y is a bivariate random vector, and they have a joint distribution. Okay, let's say they have a joint PDF, and g is another function. H, it's continuous function. Real value use function. Okay. Then the expectation of h of x, y, that is the integral of h small x, small y, multiplied by the joint distribution of x and y. Because you have here two random variables, you have to compute the double integral. Okay. So you compute the integral over the x and over the y. So if, as you can see, the definition is pretty similar. For example, let's say you have another function, let's say we have these guys, random variables, continuous random vector with join PDF like this. And the expectation of another function, x, y, and z, will be the integral of what? I need your help. Vania. This is L, okay?
Sorry, I'm not sure.
Anyone else? Junior. What would be the definition of this expectation? It's like an example. See if you understood this definition. What would be the definition of this expectation when you are working with three random variables? Ricardo?
I would say it's a free integral operation, maybe.
Okay.
Then would be E x, y, zeta times the joint PDF of x, y, and zeta.
And you take the integral all over the three. This shouldn't be difficult at all. Okay, now that we know this definition of the joint, of the expectation of a function of a bivariate vector, then we have other concepts. Let's say you want to compute the conditional expectation, okay, of H given this. This is the conditional expectation. The conditional expectation will be the integral, the same function, h, okay? So now instead of multiplying by the joint PDF, you would use the conditional PDF. And you integrate over the x. Okay, that is the definition of conditional expectation. You have any questions so far about the conditional expectation or the expectation? Just the expectation. Gabi, Abril,
Clear.
Enzo.
Everything okay, teacher.
Excellent. Okay, let's go back to the slides. Now there is another interesting concept in statistics, or in probability actually. That is independence, okay? Let's say we have two random variables, x and y. We will say that these random variables, x and y, are independent if, okay, the joint probability that x belongs to any interval and y belongs to any other interval is equal to the product of the probability of x and the probability of y. Okay. In other words, the probability of these events, that these events happens together, is just the product of the probability of these events happen independently. And given this definition, we can prove that the CDF of x and y can be written as the product of the marginal CDFs of x and y. It also holds that the joint PDF of x and y can be written as the product of the marginal PDFs. So instead of the CDF, you can replace the PDF. And this property still holds. And as a result of this, if you have two continuous functions like g and h, then g of x and h of y will also be independent if x and y are independent. Okay, so if x and y are independent, any continuous function apply to x and other continuous function apply to y, those results are also independent. So the independence is preserved under continuous functions. For example, x and y dependent. Let be the dependent random variable. Okay, let's say f is g. Okay, g g of x, h of x. X g of z squared function. Okay, the log and the square. If x and y are independent, x squared and log of y are also independent. Okay. This, for example, because the square and the log are continuous functions. Okay, these guys are continuous functions. Let's go back to the slides. That is how you apply this property. Okay, third one. Other properties about the dependence and the expectation. Okay, there is something that we call the iterated conditioning. We will use this iterated conditioning a lot throughout the course, okay? And this property says that the unconditional expectation, okay? The unconditional expectation of the conditional expectation of y given x is just the unconditional expectation of y. Okay? Then we have this property. We call this property take out what is known. And it says like this: if z is a function of x, okay, then the conditional expectation of z times y given x will be just z multiplied by the conditional expectation of y given x, because z is a function of x, which is this guy. See. And you are trying to compute the expectation using the information provided by x and this guy is a function of x, you can take out, because it's known when you are trying to compute the expectation, because the information or the conditioning here, which is x, is already known. That's why we call this property take out what is known. Okay. Finally, we have these two more properties. X and y are independent random variables. Then the conditional expectation of y given x is just the unconditional expectation. Okay, and the expectation of the product of x and y is the product of the expectations. That only happens when when x and y are independent, you can use these properties. Okay. So far, any questions about the independence, guys? The iterated conditioning. Diego Alonso, everything is fine. Alejandra.
Todo claro, profe. We have this other definition. Okay, before, when we were working with the Univari case, we talk about the expectation and the variance, okay, as the first moment and the second central moment, respectively. Now that we are working with more than one random variable, there is another concept that will appear. And this is the covariance, okay? The covariance between two random variables, x and y, we used to denote it like this. We use the Greek letter sigma xy as the notation of the covariance. And also we write the covariance as cov of x and y, and this covariance is defined as the expectation of the product of x and y minus the product of the expectation of x and y, okay? And related to this covariance, there is another concept called the correlation coefficient, or just the correlation between x and y. And this correlation is just the covariance scaled by the standard deviation of x and y. As here. We just to denote the correlation using the Greek letter rho. Okay, so rho of xy is just the covariance divided by the standard deviation of x multiplied by the standard deviation of y. And this covariance or correlation measures the linear relationship between x and y. Okay. So when the covariance is negative, we say that there is a negative linear relationship between X and Y, okay? And if the covariance is positive, we say that there is a positive linear relationship between X and Y. Remember that the covariance and the correlation only measures the linear relationship. So if you have two random variables and the covariance between those random variables is 0, then there is no linear relationship between those random variables. But that doesn't mean that there is no relationship between those random variables, because the relation can be non-linear. Okay? Covariance only measures the linear relationship. It doesn't say anything about the non-linear relationship between random variables. Okay. One more thing, the correlation by construction will always be between -1 and 1. Okay, so it doesn't have units. So you can use the correlation to compare how strong is the linear relationship between a couple of random variables. So the strength of the linear relationship between random variables can be measured with the covariance. Okay, because the covariance has units. The correlation doesn't have units. What I'm trying to say is that, for example, let's say covariance X and Y true or false?
True.
Teacher, you have to calculate a correlation first.
That's right. This is not necessarily true, because the covariance has some units. For example, check this out. let's say X is 10 times Z and Y is 10 times W. Okay, what is the covariance of X and Y? It's the covariance of Z and W is 1.
Teacher 100.
100. Okay, 100. Now let's compute the correlation of X and Y. Just for to make the example simple, say the standard deviation of p equal 1, standard deviation. Must be too much. Okay. First, what is the correlation between of these guys? And what is the correlation of these guys? The first one. You can tell the correlation between Z and W.
It's 1.
That will be 1. And the correlation between X and Y.
It will be also 1.
Then if the correlation are the same, the relationship between X and Y is the same than the relationship between Z and W. Okay. The covariance is not enough to know what is the strength of the linear relationship between two random variables. Okay, let's go to the slides. So bottom line, if you want to compute or measure the relationship, the linear relationship between the strength of the linear relationship between two random variables, you have to compute the correlation. Okay. You will never use the covariance. You only use the covariance to measure if to tell what is the kind of relationship, if the relationship is positive or negative, or if it's 0. Okay. So if the relationship is positive or negative or 0, you will use the covariance. But if you want to measure the strength of that linear relationship, you always will use the correlation coefficient. Now we have these properties about the covariance. The covariance is a bilinear operator, which means that the covariance of this sum of random variables multiplied by scalars, and another random variable will be just the covariance. This is like this, covariance between this guy and this guy first. And you can take out A because A is a scalar. So you take out A and then you get covariance between X and Y. Then you get this one. B is an scalar, so you take it out from the covariance, then you get covariance between Y and Z. And that also happens when you move this guy to the next to the comma. Then the covariance between one random variable and itself is just the variance of X. And the variance of X plus Y will be the variance of X plus the variance of Y plus another term. This is the covariance of X and Y multiplied by 2. And we can generalize these results as follows, okay? The variance of the sum of weights multiplied by random variables will be the product of those weights multiplied by the covariance of xi and xj. Okay, this must be a double sum. Or if you want, you can write this sum as the sum of the variances multiplied by the square of those weights plus 2 times the product of those weights multiplied by the covariance when I and j are different. Okay. This is very useful when we will be dealing with portfolio optimization, okay? In asset allocation and portfolio optimization, we will use this property. X will be the return. The asset return, and this is the weight. The position in the portfolio allocated to that asset. Okay. Any questions so far related to the covariance, correlation, properties? Vania? Anything on your side?
Profe, una pregunta. ¿Ese return de dónde viene? Disculpe, se me cortó el audio.
Oh. Okay. What I try to say is that this thing that looks like, okay, this is too much math for me. It's just, it has its own application, okay? The application of this generalization of the variance, we will see in the portfolio optimization. The portfolio optimization or the asset allocation, we will use this property. How does it work? So instead of X and W's, in the context of the portfolio optimization, our X here will be the asset return. And the W weight will be how much money we put we invest in that asset, okay, as a percentage of the whole wealth. Okay. So let's say we have two assets. We have two assets, okay, A and B. Let's go to the whiteboard. Markowitz, okay. A and B. Assets and are A and are B. Assets returns, okay. Let's say I want to construct a portfolio investing in those assets. Okay, the return of that portfolio will be the weight invested in the asset A multiplied by the return of that asset plus 1 minus W multiplied by the return invested return in the second asset, invested in the second asset B. Okay, this is the return. Because these guys are random variables, then the variance of the portfolio return with the variance of these guys. Plus 1. And you know how to compute this. You just need to go back to the slide and use that property. And this will be W squared or omega squared times variance of return plus 1 minus square variance of the second return asset return plus 2 times 1 minus W covariance of these guys. That is the application of that formula. Okay, that is what I was trying to say.
Gracias, profe. Más claro.
Now you can put 3 assets, 4 assets, n assets. When you have n assets, that is just the formula. And remember that this measures the risk. Portfolio risk. Okay, any more questions? Si no, podemos tomar un descanso. De 10 minutos. ¿Está bien?
Todo claro, profe.
Está claro. profe.
Buenazo. Listo, chicos. Entonces, 8:40 regresamos. Hola, hola. ¿Me escuchan?
Sí, profe, sí se escucha.
Hola, profe, sí.
Se le escucha, profe.
Ok, profe.
¿Todo bien hasta ahora, chicos? Ay, ¿qué pasó? Ya. A ver, ¿qué nos falta? A ver. ¿Pueden ver el slide?
Sí, profe, ahí se ve.
Okay. Okay, that was the correlation. Now, we will change a little bit. We will move from the random variables to data and how to construct statistics from data. Okay, let's say we have a data set like this: x1, x2 through xn. Then we can compute something that we call the sample mean and the sample variance this way. The sample mean measure, as you know, the location of data, and is just the average, okay, the simple average of those numbers. And the sample variance, which measures the variability of data, is just the average of the deviations of these guys from the sample mean, or the square of the deviations, okay? And you divide the sum by the number of numbers in this data set. Okay, you have n numbers in this data set. You divide by n minus 1. And you do that in order to get an unbiased sample variance. Okay, I forgot the square. Okay, here you have to put the square. So it's sigma hat x square, because this is the variance. Okay, I forgot to put the square. Okay. Also, we have something that we call the sample covariance and the sample correlation. Okay, those are the counterparties of covariance and correlation we defined in the previous slides. The sample covariance is just the sum of the product of the deviation of x and y with respect to the sample's mean, the sample mean of x and y. Okay, then when you compute the sample covariance, then you can compute the sample correlation, scaling the sample covariance by the sample standard deviation. What I mean is the square root of this guy for x and y. Okay. Finally, we can also compute the sample skewness and kurtosis, okay, using these formulas. So instead of using the expectations,
you will use the sample third central moment and fourth central moment scaled by the cube of the sample standard deviation and the fourth power of the sample standard deviation of the square of variance, the sample variance. Okay. In R, don't remember if we have art. Let me see. Just give me a second. Okay. Okay. Can you see the RStudio
Sí, profe.
screen? Okay. Does anyone of you know how to program in R? Camila, Minelli, Abraham, nobody. Okay. Let's create data. Create. Here, I've created a vector of consecutive numbers, okay, from 1 through 10. Okay, now let's compute the mean variance. Want to compute the mean, you have data stored in a vector in R, you just need to use the function mean. Okay, that will compute the mean of those numbers. If you want to compute the variance, use function var, that will compute the variance. Okay, this is the sample, what sample mean actually, and this is the sample variance. It's pretty straightforward. Okay, and in R you use functions. Okay, you use functions, and if you don't know how a function works, you can use you can ask the interpreter how a function works using this question mark and followed by the function name, things like this. Okay. Then you will see in the help, on the right side of the screen, there is the documentation about that function, how this function works. Okay. Let's see. And this documentation also will give you more information about other related functions like the SD function. For example, the SD computes the standard deviation. Sample standard deviation, SD of X, which is just the square root of this guy, right? Square root of the variance. So it is consistent. You can compute the standard deviation using just the function SD, or you can compute it taking the square root of the sample variance. Now, if you want to compute the skewness and kurtosis, probably you won't find a function to compute the skewness. Or the kurtosis in the standard libraries in R. It's like R, okay, the R program has a standard library, like a base package. Okay, are you with me with this explanation about how R works? Any reaction? Like,
Yes, teacher. Very okay.
okay, so R has like a base, set of functions, like these ones: mean, variance, which is var, SD, which is the standard deviation. But there are functions that haven't been programmed in the base R code, but because R is this is free software, there is a huge community that supports R. Many people who likes R, who use R for different purposes, like research or work, have developed many packages. So you don't need to reinvent the wheel. If you think about a function, probably someone else did that before you, program before you. You just need to install the package and use it. Having said that, there is a package that will help you to compute the skewness and kurtosis. The thing is that I don't remember the name of that package. Let me see. Okay, I think it's moments. So I will teach you how to install packages, okay? How to install package. You put install packages, and then you put between quotation mark the name of the package. I think it's moments. when you run the 16 line, which is this install packages parentheses moments between quotation marks, that will call that will make a request to the repository where those packages resides, and install that package into your computer. Now we have that package, you see, successfully unpack and MD5 sums check. Downloaded, blah, blah, blah. We have the package. Now, I think we can use it. Okay, now the package has been installed, but it haven't been loaded. Okay, we need to load that package. How to load? How to? Thing is, anyone can help me? I just forgot how. Okay.
Library.
Library, right? And you put moments. But when you load the package, you don't need to put the quotation mark. You just need to put the name of the package, okay? I think it's like this. Then that means that we have load that package in our workspace, and we can use it. Skewness. Now, you see, it appeared. Wonderful. And we can compute also the kurtosis. So skewness and kurtosis are functions that has been programmed in the package moments. Those functions don't exist in the base R program or code. Okay. Any questions? I know that you will work with this, how to install R, how to in your laptops, how to use it, the basis in R. If you don't know how to program in R, this has been the first time you have seen R in a class with Gonzalo. Don't worry about it. But I wanted to show you how to use R for things like the things we saw in the slide, because it's because I don't want to scare you with those formulas, okay? I want you to know how those formulas are defined, those sample mean, variance, covariance, correlation, skewness, and kurtosis. You need to know them. But in the practice, most likely you will use a program like RStudio or Python or Excel to compute that. You don't need to worry about how to compute, but you need to know, because sometimes it's useful to understand the concepts behind those formulas, or maybe someone will ask you the definition of those formulas in an interview or whatever, your work. Okay. I used to ask those kind of questions when I interview guys for intern or analyst positions. And I believe over time, more people will ask those kind of questions for quantitative positions here in Peru. It's more common in US. Okay. You mean there is a package for portfolio optimization in R. I think Gonzalo knows that package. And he will teach you how to use that package. Besides QuantMod. Okay. Any questions about R, those sample moments? About the match? Okay. Let's continue with the slides. We need to finish. Okay. We need to get these two huge theorems, okay? The law of large numbers and the central limit theorem. Those are very powerful theorems that we will use when we want to define the Monte Carlo estimator and the confidence intervals for the Monte Carlo estimator. Okay, but before we talk about the Monte Carlo, we need to talk about the estimation. Okay, now let's go back to the world of the random variables. Okay, so we went from this world to the real world. I mean real world because we were talking about data sets. Okay, that is the real world where the random variables realize. Okay, you know the random variables are functions with some properties. Okay, this is like a blueprint, but those random variables, when they realize, when you get instances of those random variables, you see data, you see numbers. Okay, so that's why we were talking about these summary statistics. But now we need to go back to the world of the random variables. Okay, and in that world, we have this random sample. Okay, a random sample of size n from a probability distributions are n independent random variables. That is a random sample of size n from a probability distribution. Are n independent random variables. You know what is independent random variable or independent random variables? Where these guys, these independent random variables, have the same distribution. Okay, these guys have the same distribution, and we used to use this notation IID. What is the meaning of IID? Can anyone tell me what is the meaning of IID in stats?
Independently and identically distributed.
Independent and identically distributed. Okay, so these guys are independent and have the same distribution. That is the meaning of IID. Okay, so now a statistic will be a function of a random sample. This is not data, okay? These guys are random variables. Dependent random variables that have the same distribution or come from the same distribution. So a statistic is a function of this random sample. We can estimate the mean of the distribution of this, the distribution that come of these guys using the sample mean. Okay, and the sample mean, we have the same formula that we have seen in the previous slides. It's the average of these guys. But instead of having data, here we have random variables. So the average of those random variables. So this guy is a function of a random sample. So this guy is a statistic. The sample mean is a statistic. And as we can have sample mean, we also can talk about the sample variance. And the sample variance will be computed in the same way, but instead of having data, we have this random sample here in the definition of the sample variance. And the sample variance is an estimator or an statistic. In this case, an estimator of the population variance sigma square, which population variance is the variance of the distribution that is behind this random sample. Okay. Now, let's say theta hat is an estimator. Okay. And if this guy is an estimator, there are two metrics. The first one is the accuracy of the estimator, and the accuracy of this estimator will be measured by the bias of theta hat, and the bias is defined as the expected value of theta hat minus the true value of theta hat. Remember that theta hat, since it is a function of a random sample, theta hat is also a random variable. So a statistic or estimator is a random variable. That's why we can compute the expectation. Okay, so the accuracy measures the bias of the estimator, while the precision will measure the variance of the estimator. So the precision measures the variance, the accuracy, the bias. The standard deviation of an estimator is also called the standard error, and we used to use this notation as E of theta hat, standard error. This initials stands for a standard error. And I think you have seen this before. When you have read a paper about econometrics regression. You have seen this, something like this. Right? The coefficient and the standard error, which is just the standard deviation of this guy. Right? In linear regression is likely you have seen this. And finally, since this guy is a random variable, we can talk about the sampling distribution of our estimator. So there is a sampling distribution for this guy. We have 8 minutes. Let's talk about these theorems. The law of large numbers. Okay, the law of large numbers says, let's say we have a random sample. Okay, from a distribution with finite mean mu. Okay, we just need that the distribution that is behind this random sample have a finite mean. If this distribution has a finite mean, then the limit when n goes to infinity of the sample mean will be the true mean, almost surely. Okay. So when you increase the size of your random sample, the sample mean will convert to the true mean, the mean of the distribution. All right? That is the law of large numbers. Then, and finally, we have this theorem, the central limit theorem. In this case, we also have a random sample, and this random sample comes from a distribution with finite mean and finite variance. We add this property or this condition. We need a distribution. The distribution behind this random sample should have finite variance as well as a finite mean. Then, if that is the case, then the standardized sample mean the sample mean minus the true mean divided by the standard deviation, the true standard deviation divided by the square root of the sample size, this random variable will converge in distribution to the standard normal distribution. When the size of your random sample increases or goes to infinity. Okay, so when you increase the sample size of your random sample, the distribution, the sampling distribution of the sample mean will converge to the normal distribution. As you can see, we are not saying that the distribution behind this random sample should be normal. It could be any distribution. Any distribution. You can think of a binomial, Poisson, chi-square, T distribution, Gauss distribution, logistic distribution, whatever distribution you can think of. When the size of this random sample increases a lot, the sampling distribution of your sample mean will converge to the normal distribution. That is the strength of this theorem.
See if I can give you a visual proof of what we have learned. Okay. Look at this. Yes. Can you see the interface of R Studio on the screen?
Yep.
Awesome. In R, because many things has been programmed, you can simulate random variates, okay, random numbers. You can simulate random numbers. If you go to Google, you can look up for something like, what is this? R intro, I mean, it's introduction to R. And if you type introduction to R, look at this. If you type introduction to R in the Google search R, then you can see this cranrproject.org. Okay, this is an introduction to R, a comprehensive R archive network. Here you will see this, an introduction to R. This is the version 4.1.3, 2022, March 10. In page 27, okay, here, 33. Probability distributions, okay? Probability distributions, let's see. Here, you see the distributions that have been programmed in the base code of R, okay? So there is this beta, binomial, Cauchy, chi-square, exponential, F, gamma, geometric, hyper, geometric, log normal, logistic, negative binomial, normal, Poisson, sign rank, student, uniform Weibull, and Wilcoxon. I haven't used this Wilcoxon distribution. Anyways, this distribution have been programmed now. So you can simulate numbers from these distributions. You just need to use the R name of these distributions. And you need a prefix. If you want to simulate numbers, you would use the prefix R for simulation of random deviates or variates, okay? So you follow this R for the name of by the R name of those distributions. For example, if you want to simulate random deviates from the normal distribution, you use R norm. Okay, if you want to simulate from the binomial distribution, you use R binom. Okay, so let's go back to R.
Now, for to see the example, here I'm simulating from the binomial distribution. Okay, the binomial distribution needs two parameters: the n, this the size of the binomial distribution, and the probability. Okay, here I will simulate. Okay, x. So x is these guys are random deviates or random variates or random numbers that have been simulated from the binomial distribution, where the probability of success in that binomial distribution is 0.5, 50%. So this is the result of simulating numbers, flipping a coin, a fair coin. Okay. Then I'm computing the mean of those x of these vectors and storing the mean in this vector called x bar. So this x bar is a vector of means. How many? A lot of these guys. 10,000. So I have 10,000 means. Now I will compute the true mean and the true standard deviation to compute the this standardized random variable, which is x bar, our sample mean, minus the true mean divided by sigma divided by the square root of n, which is, if you want to compare this, let's go back to the slides. This guy. I'm computing this guy for many random samples. Okay. And then I will plot this guy. It's a vector. I will plot the histogram of this vector. Okay, and I will also add, I will plot the normal distribution, okay, over that plot. And you will see this is the distribution in bars, the histogram of this guy, Z, which is our scale sample mean. And in blue, that is the normal density. This guy have been generated using binomial random numbers. However, the distribution of the mean will look like the normal distribution. We haven't used here normal distributions or normal random variables, but because of that theorem, the sample mean will converge in distribution to the normal distribution, which is a powerful result. Actually, it's amazing. You can change here the random simulator. You can use uniform, you can use Poisson, you can play here. And you'll see that this also happens. The plot in the right hand side. Well, any questions so far?
Teacher, sorry, can you explain again the code, please?
The code, okay. This is, first I set the random seed, so you can reproduce the code, set the probability of success in the binomial distribution. This is the size for the binomial distribution, which means this is like a Bernoulli distribution because the size is 1. Then I set some numbers to m is the number of means. This is a for loop where I sample 100 random numbers from the binomial distribution. So this is our x1, x2, x3, up to x100. Then I compute the mean here and store it in this x bar. And I do this m times, which means is 10,000 times. So I store 10,000 means in this vector x bar. Then I compute the true mean and the true standard deviation from the binomial distribution we are using here, and scale the means by the true mean and the true standard deviation using the formula that we have seen in the theorem. Then I plot the histogram of this guy, set as an argument true to plot the probability, and then we add the normal distribution. I compute the normal density using this set of x and add as a lines x and y. And I put it in blue, and the thickness of these lines is 2. And that's it.
Okay, so teacher, for example, in this case, first you start like simulating a binomial distribution, and you, like in this code, in the line 12, you get like a lot of means of x, and you store it in x bar.
Yes,
so in the
that's right.
line 18, like you are doing this theorem that we had seen, that when you have like a lot of numbers and you like use this formula, you approximate the distribution to a normal distribution. That's okay? That's right?
Yeah,
Okay.
that's right. I would share with you this code, okay? So you can look at it. All right. Se acabó el tiempo. Lo siento, chicos. Yo sé que querían quedarse fácil un par de horas más.